Okay, so I want to continue on and think about how basic trigonometry can be extended into other areas, specifically more generalizable to non-right triangle triangles. So what I did here is I took a regular triangle and I split it into two triangles. This is not meant to be two equal triangles. I kind of tried to draw it a little bit askew and whatever. It doesn't matter. I mean, any time I have a triangle, I can always, uh, find a line here to cut down and make this into two right triangles. So there's a right triangle, there's a right triangle. Even if it was extended over kind of leaning backwards, let's do something that's more than like this. I can still find a place. Like I'm not going to go this way. I'm going to go this way to find a place where I can cut this into two triangles. So the key here is that if I think about the sine of both theta and phi, sine theta, sine phi, they both have h in them, right? This is going to be h over x. This is going to be h over y. And so what I can do is I can solve x sine theta equals h, y sine phi equals h. And now I can put these together because h has to be equal to h. So in other words, x sine theta equals y sine phi. And now with a little bit of manipulation, let's divide by xy on both sides. We end up with the basic concept of the law of sines, which is that the angle, now I'm going to take out the h, the angle across from the side form a ratio pair that's equal regardless, and I'm throwing in the other one here by extension. So I call this z, and I'll call this, how about alpha? So tacking on the third one, it would be sine alpha equals, sine alpha over z. That's the third ratio pair. So this is called the law of sines. And it doesn't matter who's on top and who's on bottom. I could have y over sine theta, x over sine phi, z over sine alpha. What matters is that I have this pair partnership, and it generally reinforces the understanding that the larger the angle, the larger the side it has to be across from. So that's true in any triangle, that if you look at the order of the lengths of the sides, the angles that they're across from will go in the same order. So we can use this to solve triangles that are not right angle triangles, right triangles, but have given us three pieces of information, with two of them being a side and an angle that's across from that side. So let me give you an example on how it would work. So if I've got a triangle and I know this is 40 feet and this is 37 degrees and this is 60 feet, then I can figure out this, this, and this. Let's look at how the law of sines gets in here. So we say sine 37 over 40. That's the pair that I have. And then I'm going to have some labels here. So I'll call this X. I'll call this A. I'll call this B. So the other one, the place I'm going to get started is with the A and the 60. So sine of A equal over 60 has to be equal to the sine of 37 over 40. So I can solve this now. 60 times sine 37 divided by 40 equals sine A. And at this point, I need to bring in a tool from my toolbox, which we haven't used yet, which is finding the inverse sine. And we're going to talk about that in a different video because I want to focus on that problem kind of separately. So let me rewrite this problem so that we have two angles. Let me show you a couple different ways that that'll show up. And then all we're doing is finding the missing side. So if this is 32 degrees and this is 96 degrees and this is, I don't know. And then let's say this is 50 feet. And then I want to figure out this, this, and this. So in this problem, again, I've got I've got 50 over sine 32. Notice I'm writing it in the other orientation with the side on top. Really doesn't matter. This side I'm going to call x, x over sine 96. And now I can solve this problem. This is just a proportional problem. So 50 times sine 96 equals x times sine 32. Notice that I'll kind of leave that in its exact form as I go through and solve it. Doesn't really matter. I can turn them into decimal representations. But at this point, I haven't had to do any rounding along the way. So that's kind of nice. I just type this directly into my calculator and do one rounding instead of doing multiple roundings. Make sure your calculator is set to degree mode because we're looking at degrees here. So this means that the x value I'm getting would be 93.8. I'm just going to leave it to 1/10 of a foot. So I figured out that side. Now let's think about this other pair. I can't use the Pythagorean theorem because this is not a right triangle, but I can use the fact that these three angles have to add up to 180. So 32 plus 96 plus question mark has to be 180 degrees. So therefore the missing angle would have to be 52 degrees. So once I've got that pinned down, then I can find this missing side here. And again, you can do it with whatever you want. You could use the 93.8 and the sine 96. I'm going to go back to the 50 over sine 32 just because it leaves me with exact numbers that I didn't have to round, which give me my best answer. So the third pair here would be y over sine 52. And so 50 times sine 52 divided by sine 32 equals y. Sorry, just check on this. So then y equals whatever that is. 74.4 looks like, rounded to the nearest tenth. So law of sines works for a lot of triangle problems because, and it can even be generalized to right triangles. It's kind of overkill with right triangles because when you're doing the sine of 90, the sine of 90 is equal to 1. And so then it kind of boils down to our basic trig relationship. A slightly harder version of this problem is where the only side that's given is a cross. So let's say this is 95 degrees, this is 20 degrees, and then I get that this side is 100 feet. So again, I can still use the law of sines here, but I have to supply that missing angle first to even get started, right? Because I don't have a pair. If I look across, each side angle is missing a piece of information. I don't know the length of that side. I don't know the length of that side, and I don't know the size of this angle. But of course, you can know the size of that angle because 180 minus 20 minus 95 gives me what, 65? Yeah. So then I can set it up. 100 feet over sine 65 equals x over sine 95, or 100 over sine 65 equals y over sine 20, where this is x and this is y. So that's the basic intro to the law of sines and the derivation of where it comes from. And that's a very powerful tool in your toolbox.